When people talk about the greatest scientists in history, especially in physics, who comes to mind? Who are the individuals whose discoveries fundamentally changed our understanding of the universe? If you asked the B-Bar Bilam audience, you would hear a remarkable range of names. They'd probably mention Max Planck, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Max Born, Alessandro Volta, Hans Christian Ørsted, Alexander Graham Bell, and many others without hesitation. But stop someone on the street, someone who remembers at least a little from high school physics, and the first two names you'll almost certainly hear are Isaac Newton and Albert Einstein. Ask for a third, though, and things get a lot harder. Yet there is another giant of science whose name rarely gets the recognition it deserves. A man whose influence stands shoulder to shoulder with Newton and Einstein, and arguably made Einstein's greatest achievements possible. A scientist Einstein admired so deeply that he kept his portrait on the wall of his office. James Clerk Maxwell, doctor. Do you know what Einstein said about him? Speaking about the theory of special relativity, the work that forever changed physics, Einstein wrote, "The special theory of relativity owes its origins to Maxwell's equations of the electromagnetic field." He went even further, saying that since Maxwell, physical reality had come to be understood in terms of fields rather than isolated objects, calling that shift in perspective the most profound change in physics since Newton. And Einstein wasn't alone. Maxwell's biographer, Ivan Tolstoy, argued that Maxwell's influence on science rivals Einstein's and even Newton's, whose discoveries Maxwell's own work would ultimately expand upon. Professor R.V. Jones, describing Maxwell's landmark paper presented to the Royal Society, called it one of the greatest scientific achievements in history because it provided the first real evidence that light and radiant energy were part of the same underlying phenomena. Max Planck, the father of quantum theory, praised Maxwell for accomplishing something entirely unprecedented. And then there's Richard Feynman, one of the greatest teachers physics has ever known. Feynman believed that if people 10,000 years from now looked back at the 19th century, they would almost certainly regard Maxwell's discovery of the laws of electrodynamics as its single greatest scientific achievement. Those are extraordinary endorsements. So why is Maxwell's name mentioned so rarely? Why doesn't he receive the same recognition as Newton or Einstein? I'm not sure anyone knows for certain. But while researching his life, I came across an observation that stuck with me. Perhaps historians have often overlooked Maxwell simply because they never fully grasped the magnitude of what he accomplished. So, who was this man? What did he discover that earned praise like this from some of the greatest scientific minds in history? Today, it's time to give James Clerk Maxwell the recognition he deserves. And like Michael Faraday before him, Maxwell's story has far more to teach us than just physics. In fact, there's a reason I made a video about Faraday before this one. Maxwell's story begins where Faraday's leaves off. He didn't replace Faraday's ideas, he built on them and carried them to an entirely new level. Even as a teenager, Maxwell was extraordinary. At just 14 years old, he had already published a paper on geometry. He had an unusual habit of trying to explain everything he observed through mathematics, and he was remarkably good at it. By the time he entered the University of Cambridge at 19, he had already published 3 scientific papers. And before long, scientists across Britain were beginning to recognize his talent. Then came Saturn. You know those magnificent rings surrounding the planet, one of the most spectacular sights in our solar system. For centuries, no one knew what they actually were. Some believed they were liquid. Others argued they formed one enormous, solid ring. Everyone had a theory, but no one had convincing evidence. Then in 1857, a scientific competition was announced. A prize would be awarded to anyone who could correctly explain the true nature of Saturn's rings. And once again, James Clerk Maxwell stepped forward. Maxwell demonstrated that Saturn's rings could remain stable only if they were made up of countless tiny particles, each orbiting under the pull of gravity. And he didn't just suggest the idea, he proved it with extraordinary mathematics. This is what I mean when I talk about Maxwell's gift for mathematics. Saying Saturn's rings are made of particles is one thing. Describing their motion with equations, predicting their behavior mathematically, and showing why every competing explanation fails is something entirely different. That ability to translate nature into mathematics is what set Maxwell apart. Remarkably, he was also the only scientist who entered the competition. The achievement quickly made him a rising star in the scientific community. Before long, many were calling him one of Britain's finest theoretical physicists. It came as no surprise when, at just 25 years old, he was appointed professor at Marischal College in Aberdeen. But before we arrive at the discoveries in electromagnetism, the work that would ultimately change the world, there's another obsession of Maxwell's that led to an equally remarkable breakthrough. Colors. In our video about color, we talked about how Isaac Newton discovered that white light contains all the colors of the spectrum. But Newton never fully explained how colors combine to create entirely new ones. And for nearly a century and a half, very few scientists seriously pursued the question. One notable exception was Thomas Young. He believed the answer lay in biology. Young proposed that the human eye contains 3 different kinds of receptors, corresponding to the primary colors. It was a brilliant insight, but turning that idea into a complete scientific theory required someone with Maxwell's mathematical talent. Using a surprisingly simple device called a color wheel, Maxwell began conducting experiments with friends and colleagues. He discovered that when the colored sections spun fast enough, the eye could no longer distinguish the individual colors. Instead, the brain blended them together, creating entirely new colors that weren't physically present on the wheel. From there, Maxwell developed mathematical formulas capable of predicting exactly what color would appear when the 3 primary colors were mixed in different proportions. In other words, he became the first person to mathematically describe the color relationships that still form the foundation of modern digital color systems, including the color values used by software like Photoshop today. But he didn't stop there. Building on that theory, Maxwell accomplished something even more remarkable. He created the world's first permanent color photograph. This is that photograph. In 1861, while delivering a lecture on color at the Royal Institution, Maxwell reached the point where he explained that every visible color could be produced by combining 3 primary colors. Then he projected this image onto a screen for the audience. To the people sitting in that room, it must have felt like magic. In reality, they were witnessing the beginning of the digital world we now take for granted. The red, green, and blue color model Maxwell demonstrated, the RGB system, is the very principle behind the screen you're watching this video on right now. Every smartphone, computer monitor, television, and tablet relies on the same fundamental idea. And Maxwell achieved all of this before turning 30. At just 29 years old, he became one of the youngest scientists ever elected to the Royal Institution. Then, almost unbelievably, everything changed. Marischal College, where he had earned his professorship at 25, merged with another university in Aberdeen. Because another professor had greater seniority, Maxwell lost his position almost overnight. He was suddenly out of work. His personal life had been difficult as well. Maxwell was an only child. His mother died when he was just 8 years old, and only a few months before becoming a professor, he lost his father too. A deeply emotional man by nature, Maxwell wrote poetry, loved literature, and possessed the soul of an artist as much as that of a scientist. After losing both of his parents, he found himself feeling profoundly alone. During that difficult period, he met Catherine, the woman who would become both his wife and his greatest source of encouragement. He proposed to her with a poem, and the two were soon married. While searching for another academic position, Maxwell spent time managing the family estate. After being rejected by several universities, he finally accepted a position at King's College London. It was there that the most important chapter of his scientific career truly began. His fascination with electricity and magnetism intensified, although in truth, that fascination had started much earlier. Since childhood, Maxwell had been captivated by electricity and carried out experiments whenever he had the opportunity. Humanity itself had been fascinated by electricity for centuries. Lightning, in particular, inspired endless curiosity. Figures like Benjamin Franklin, whose portrait still appears on the $100 bill, and who would later become one of America's founding fathers, famously flew kites during thunderstorms in an effort to better understand electricity. Magnetism, meanwhile, was already changing the world in practical ways. Sailors had relied on magnetic compasses for generations, using Earth's magnetic field to navigate across the oceans. But as we discussed in our video about Faraday, almost no one recognized that electricity and magnetism were actually connected until Michael Faraday came along. Remember Faraday? He had made astonishing breakthroughs in electricity and magnetism, opening an entirely new chapter in science. He demonstrated that electricity could produce a magnetic field and that changing magnetic fields could generate electric current. For the first time, someone had shown that these weren't separate forces at all, but different expressions of the same underlying phenomenon. The problem was that Faraday couldn't fully explain why. He had no mathematical framework to describe what he was observing. Mathematics simply wasn't where his greatest strengths lay. That's where James Clerk Maxwell entered the story. Maxwell became convinced that there had to be a mathematical relationship connecting electricity and magnetism. While teaching at King's College London, he devoted himself almost entirely to uncovering it. In the simplest sense, he believed Faraday was right. He just needed to prove it. After years of work, Maxwell arrived at 4 equations that would permanently transform physics, equations we now know as Maxwell's equations. At first glance, they're intimidating. Even after they've been rewritten into their modern, simplified form, they aren't exactly light reading. But as you've probably noticed by now, our focus isn't on memorizing formulas. What matters is understanding the ideas behind them. Once you understand the ideas, the mathematics begins to make sense. The first equation, commonly known as Gauss's law, describes how electric charge creates an electric field. The second, Gauss's law for magnetism, tells us that magnetic poles never exist by themselves. Every magnet always has both a north and a south pole, making the net magnetic charge effectively zero. The third equation may already sound familiar. It's Faraday's law of induction, and it tells us that a changing magnetic field creates an electric field. The fourth, known as the Ampere-Maxwell law, explains the opposite relationship. An electric current, like the one flowing through a wire, creates a magnetic field. But Maxwell's greatest insight didn't come from any one equation by itself. It came from putting all 4 together. As he worked through them, he realized something was missing. To make the mathematics internally consistent, he introduced one crucial addition to the final equation. That single correction revealed something extraordinary. Changing electric fields generate magnetic fields, just as changing magnetic fields generate electric fields. Think about what that means. A changing magnetic field produces an electric field. A changing electric field produces a magnetic field. Each one continuously creates the other. With just a handful of equations, Maxwell had captured one of nature's deepest secrets. Electricity and magnetism weren't independent forces at all. They were inseparable, constantly interacting, almost like reflections of one another. Together, they formed a single unified phenomenon, electromagnetism. With that achievement, Maxwell established himself as the world's leading theoretical physicist. His reputation spread rapidly, and he became one of the most respected scientists of his era. But curiosity never allowed him to stop. Using those same equations, Maxwell turned to another remarkable idea that Michael Faraday had proposed years earlier. We briefly mentioned this in our Faraday video. Faraday believed that light was a kind of vibration, traveling along invisible lines of force. He even suggested that those force lines might be what hold matter itself together. To most scientists at the time, the idea sounded absurd. Invisible lines of force? Like hidden wires stretching through empty space? People dismissed it as pure speculation. Yet Faraday had a vivid mental picture of how it might work. He imagined particles connected by invisible force lines, with a vibration at one point traveling through those connections as a wave. The astonishing part is that he imagined all of this without having any mathematical proof. That alone tells you how extraordinary his scientific intuition really was. But intuition wasn't enough. Someone had to show whether the idea was actually true. Maxwell was one of the few people who looked at Faraday's vision and thought, "This makes perfect sense." He combined Faraday's remarkable intuition with his own extraordinary mathematical ability. As Maxwell worked through his equations, they revealed something unexpected. Electromagnetic disturbances could travel through empty space as waves. Naturally, that raised another question. How fast would those waves travel? So Maxwell began calculating. And this is where the real magic happened. As he combined all of his equations, he noticed a relationship no one else had seen. It was the connection Faraday had sensed but could never demonstrate. When Maxwell combined the fundamental constants governing electricity and magnetism, the mathematics produced the square of a speed. A speed. But what speed? What in nature could possibly travel that fast? The answer came out to roughly 300,000 kilometers per second. The answer was astonishing. It was the speed of light. Scientists had already measured the speed of light long before Maxwell. But the fact that this exact value emerged naturally from his equations meant something extraordinary. It meant Faraday had been right. Light itself was an electromagnetic wave. For the first time in history, science wasn't just measuring light, it was explaining what light actually is. That discovery changed everything. It challenged and expanded the foundations laid by Newton, forcing physicists to rethink many of their assumptions about how the universe works. More importantly, Maxwell's work introduced an entirely new concept to science: electromagnetic waves. It would eventually change the world. Ironically, Maxwell now found himself in the opposite position from Faraday. Faraday had experimental evidence but lacked the mathematics to fully explain it. Maxwell had the mathematics, but he couldn't experimentally prove what his equations predicted. When he began claiming that invisible electromagnetic waves traveled through empty space, many scientists reacted with skepticism. To them, these unseen waves sounded no more believable than Faraday's invisible lines of force had years earlier. Then, about 20 years later, a German physicist named Heinrich Hertz finally demonstrated that Maxwell's predicted electromagnetic waves were real. Suddenly, Maxwell's theory was no longer just beautiful mathematics. It was reality. So what? That's fascinating. But what are electromagnetic waves actually good for? Hertz himself famously replied, nothing. As far as he was concerned, they simply confirmed that Maxwell had been correct. History would prove him spectacularly wrong. The waves Hertz had produced were radio waves. Within only a few years, Guglielmo Marconi used those same waves to develop radio communication. Not long afterward came television. Then engineers began using higher frequency radio waves to create radar, transforming navigation, aviation, weather forecasting, and countless other technologies. After that came microwaves. Most people recognize them from the kitchen, but their greatest impact has been something far bigger: wireless communication. Without microwave transmission, modern cellular networks simply wouldn't exist. Then came infrared waves, making thermal imaging and remote controls possible. Ultraviolet light followed, becoming invaluable in scientific research, medicine, and sterilization. Then came X-rays, revolutionizing medical diagnosis. And then gamma rays, which are now used in cancer treatment, medical technology, and food sterilization. Every one of these technologies traces its roots back to the equations Maxwell published more than 150 years ago. But entire industries, entire fields of science, much of modern technology, all built upon a few pages of mathematics. Perhaps that's also why Maxwell never became a household name. During his lifetime, he was talking about things no one could see or touch. And he never lived long enough to witness the incredible technologies his ideas would eventually create. After these revolutionary achievements, Maxwell returned to his family's estate. You might imagine that he finally settled into retirement. He did not. Instead, he turned his attention to thermodynamics, another field in which he would leave a lasting mark. After several years of independent research, the University of Cambridge invited him back to establish a new laboratory. That laboratory became the famous Cavendish Laboratory. Its impact on science would be extraordinary. The electron would later be discovered there. Fundamental breakthroughs in atomic physics would emerge from its halls. In 1953, researchers used X-ray diffraction to help reveal the structure of DNA. Over the decades, work carried out there would contribute to 29 Nobel Prizes. But Maxwell himself would never see any of it. After returning home once again, he developed the same illness that had taken his mother's life years before. At only 48 years old, James Clerk Maxwell died of stomach cancer. A remarkably short life. An extraordinary legacy. And we've only scratched the surface of everything he accomplished. I hope this video has helped explain why Maxwell is regarded as one of the greatest scientific minds in history, and just how profoundly his work continues to shape our lives. The technological impact alone is almost impossible to overstate. But perhaps his greatest contribution was something even deeper. He changed the way humanity looks at the universe. Instead of focusing only on the things we can see and touch, Maxwell revealed the invisible structure beneath reality itself. In many ways, that's exactly what I've been trying to do throughout this series. As we journey from classical physics into quantum mechanics and beyond, my goal isn't to overwhelm you with equations. It's to first understand the ideas behind them, to tell the story in a way that anyone can follow. We'll continue moving backward and forward through history whenever the story demands it, connecting the discoveries that shaped our understanding of the universe. My hope is that, by the time this series is complete, it will become one of the most comprehensive guides to physics available for anyone who simply wants to understand how our universe works. And maybe, just maybe, it will inspire someone watching. Maybe it will encourage someone to ask the right questions. Maybe it will motivate someone to make the next great discovery. Maybe someone watching today will help change the world tomorrow. And as always, until next time, thank you for being here. Take care.